Alright, this is a video that you should watch on Monday, March 6th for Tuesday, March 7th class. This is going over material, part of the material from section chapter 6-2, and we need to remember a couple properties of radicals. So let's remember these two properties. So first, if we have some nth root of a times b, that's going to be equal to the nth root of a times the nth root of b. We've seen this before, back when we simplified radicals a few months ago. Okay, a second property that we need to remember is if we have the nth root of some value a divided by b. Well, we could write this as the nth root of a divided by the nth root of b. Okay, these two properties are properties of radicals. The first one is the product property, because you can see we're multiplying. And then this one's the quotient, because we're dividing, a divided by b. Okay, so we're going to need to use these two things to do what we're going to work on tomorrow in class, which is simplifying radicals. But in this case, we'll be simplifying radicals where it's not just a square root, meaning n is 2, but values other than 2. So cubed roots, fourth roots, fifth roots, those types of things. So the directions are to simplify. Okay, we're going to look at 3 products and then 3 quotients. So example number 1. Case, let's remember, let's do a basic one first to jog our memory. The square root of 32. Now this is a square root because the n value is 2. If it's 2, we don't write it, so we know that this is a square root. Okay, the square root of 32. Well, 32 isn't a perfect square, but we can simplify it by asking, are there any perfect square factors of 32? And there are. So I'm running out of lead here. 32 has a perfect square factor of 16. So I can write this as the square root of 16 times 2. 16 times 2 is 32, which then I can use this product rule and separate this into the square root of 16 times the square root of 2. And the square root of 16 is a perfect square. Well, that's 4. So 4 root 2. Okay, so we did those types of problems before winter break. Let's see how we can apply that same thinking to a radical whose index is something other than 2. So here we have a 3. So this is the cubed root of 108. Well, the cubed root of 108, if we do that on our calculators, we see we get a decimal, meaning 108 is not a perfect cube. But we must ask, does 108 have any perfect cube factors? If so, we can simplify it. Well, if I go into my calculator, what are my perfect cubes? Well, like 2 cubed is 8. So I want to see, is 108 divisible by 8? No. What's another perfect cube? Well, 3 cubed is 27. So 27 is a perfect cube. Let's see if 108 is divisible by 27. Okay, it is. 27 times 4 is 108. So that means I can rewrite this as the cubed root of 27 times 4, which then I can separate this into the cubed root of 27 times the cubed root of 4, which is 3 times the cubed root of 4. The cubed root of 4 cannot be simplified anymore, so there we have it. We are done. Okay, let's do one more of these where we have a variable as well. So let's look at the 5th root of 32x to the 10th. Alright, similar process, but now we see we have a variable as well. Well, let's look at the number first, 32. 32 actually is a perfect fifth, meaning what number to the 5th power is 32? Well, 2 to the 5th power is 32. I can write this as 2 to the 5th. 2 to the 5th is 32. Now I'm going to do the same thing with this x. I'm going to say x squared to the 5th is the same thing as x to the 10th, right? X squared to the 5th, 2 times 5 is 10. That's the same thing as x to the 10th. I can then use my product rule up here to separate this radical into two radicals. This is the 5th root of 2 to the 5th times the 5th root of x squared to the 5th. Well, what's the 5th root of 2 to the 5th? 2. What number times itself 5 times is 2 to the 5th? 2. What we'll see is if the index and this exponent inside are the same, they cancel out. Right? The 5th root of 32 is 2. And then here, this 5 and this 5 cancel. The 5th root of x to the x squared to the 5th is x squared. Okay, so that's an intro to simplifying nth roots. Now let's look at when we have to use this quotient rule. Okay, so I'm going to kind of separate. Now we're looking at when we're going to use the quotient rule. Directions are still the same. Simplify. Okay, so say we have the square root of 3/5. Okay, back before winter break we learned that, hey, this is a problem. We don't like having fractions under our radicals. We need to rationalize this. And we did that by multiplying by 5 over 5, which creates a perfect square in the denominator. This becomes the square root of 15 over 25. We see 25 is a perfect square. I can write this now using the quotient rule. I can separate that radical into two radicals, square root of 15 divided by square root of 25, which is the square root of 15 over 5. And now we're okay, because we no longer have a fraction under the radical, and we no longer have a radical in the denominator. Okay, so hopefully that rings a bell of what we've seen in the past. Let's now see how we can apply this when the index is no longer 2. Sorry for the video. Seems like it's skipping a little bit, but hopefully my voice is coming through. So let's look at the 4th root of 7/8. Okay, the 4th root of 7/8. Alright, we still have the same problem. We don't like having fractions underneath a radical. So I need to create not a perfect square in the denominator, but a perfect 4th. So I need to think 8 times what is going to give me a perfect, not perfect square, but a perfect 4th. Well, 16 would do that. So I'm going to multiply by 2 over 2, and you'll see in a minute why this works. So this becomes the 4th root of 14 over 16, which is equal to, using the quotient rule, the 4th root of 14 over the 4th root of 16. Well, now look what happens in the denominator. What number to the 4th power is 16? 2. 2 to the 4th power is 16. So by multiplying by 2 over 2 initially, that created a perfect 4th in the denominator. So I could take the 4th root of 16 to get 2. There we've rationalized this particular fraction. Last one. Number 6. Here we go. We've got the cube root of m cubed over n. Okay, so let's see what happens here where we've got variables. And once again, we don't like having fractions under our radicals. So I need to multiply by something that's going to give me a perfect, sorry that's skipping, that's going to give me a perfect cubed in the denominator. Well, right now I have n in the denominator, so I need to multiply by n squared. That's going to give me the perfect cube n cubed in the denominator. So this is m cubed n squared over n cubed, which then I can use my quotient rule to separate this into two radicals. And now we see, okay, in the numerator I have the cube root of m cubed times n squared. Well, that's a product, so I actually want to use the product rule here. So that's the cubed root of m cubed times the cubed root of n squared divided by, well, down here, the cubed root of n cubed is just n. These cancel. And finally, in the numerator, the cubed root of m cubed, those cancel. So I have m times the cubed root of n squared over n. Okay. Alright, so be prepared to have these notes with you at the beginning of class tomorrow. We will have a quick quiz on these. If you have these notes, you will be totally fine. See you tomorrow.